Okay, so in this type of problems, whenever I see such an integrand, you observe that there is a seventh power of z here, and this is the eighth power, and we know that the derivative of z raised to 8 is 8 z raised to 7. So this is one of the big hints that will help us in solving this problem. Now, let me carry over to the next page. So I look at 1 over integral 2 pi I integration z raised to 7 5z raised to 8 plus 3 dz, and this integration is over a unit circle. Now this reminds us of our standard argument principle. The argument principle says that whenever I have 1 over 2 pi I integral the derivative of the function, let me write it f dash z upon fz dz over the curve gamma, this is equal to number of zeros minus number of poles inside gamma. Okay, now here when I in this problem, when I take 1 over 2 pi I and I pull out this 5, so this will become 1 by 5 integral z raised to 7 z raised to 8 plus 3 by 5 dz, and the derivative of z raised to 8 is 8 z raised to 7, so I'll multiply and divide by 8 also. Okay, and now this looks like f dash and this looks like f, and now we are going to look at this of this polynomial denominator. So I'm writing number of zeros minus number of poles of the function f inside gamma. So we are going to look at z raised to 8 plus 3 by 5 inside this unit circle mod z equal to 1. If you look at z raised to 8 plus 3 by 5 equal to 0, you have to find the 8 roots of this particular polynomial and you have to check where the roots are. Now these 8 roots I'm going to show you geometrically. So these are the roots of the equation z raised to 8 plus 3 by 5 is equal to 0. They are actually lying on the circle x square plus y square equal to 0.938, where 0.938 is the value of 3 by 5 raised to 1 by 8. So these 8 roots are actually lying inside the unit circle, as you can see in the figure. So now we will move ahead. So here fz is equal to z raised to 8 plus 3 by 5. Now this is a polynomial, so the number of poles will be 0. So this function has no poles. So when I'm going to evaluate the integration, the number of poles I'm going to write as 0. Now what are the roots we have already seen? So how are we sure that all these roots are inside the unit circle? So if alpha is the root, this means alpha raised to 8 plus 3 by 5 will be certainly equal to 0. This means alpha raised to 8 is equal to minus 3 by 5. When I take the magnitudes, I will get mod of alpha raised to 8 is equal to 3 by 5, which is less than 1. So this means that mod of alpha is certainly less than 1. So, but alpha is any root of this polynomial, and we got that this alpha has to be a complex number with magnitude less than 1. So here I'm pretty sure that all roots are inside the circle mod z equal to 1. So this means that the number of zeros that are inside the circle mod z equal to 1 mod this will be equal to how much? This will be equal to 8. So I will use this in the integration now. Therefore, when I write that integration in this format, now I understand that this is nothing but 1 by 5 into 1 by 8 into 1 upon 2 pi I integration over the curve small circle mod z equal to 1. This is f prime, this is f dz, and this is equal to 1 by 5 into 1 by 8 1 over 2 pi I f prime upon f is number of zeros. How many zeros we got inside the unit circle? We got 8 zeros. And how many poles were there of the function f inside the unit circle? There were no poles, so this will become 8 minus 0, and therefore this finally this solution will become 1 by 5. So I'll repeat how we got this 8 minus 0. This is by argument principle. This is nothing but number of zeros inside the curve minus number of poles inside the curve of the function f. I hope now this problem is understood.